Hey guys, this video will take you through a worked explanation of the example that runs over the 3 pages in our notes here. So here we have the 4 students who have got together to design and construct their outfits for the end of year school social, and the graph shows the tasks and the times taken to complete by each student in hours. So we can see Vanita can do designing in 8 hours, purchasing material will take her 10 hours, 6 hours for the cutting out, and 5 hours for the sewing, and so forth for each of the 4 people and each of the 4 tasks. So Vanita, Stan, Ebony and Philip only want to perform 1 task each and get the outfits made in the shortest time possible. How long will the project take? So when you see something like this allocation style problem, our Hungarian algorithm is the thing that is going to help us identify the answer in that systematic way. So our first step is to create our cost matrix. And so in this example, we don't have a table of the times for each task for each person. So we transfer that information into a matrix form. We have 4 people and 4 tasks. So that means we're going to have a 4 by 4 matrix. So this cost matrix is always square. And we tend to put the people, or the left-hand side of the bipartite graph, as our row headings, and the tasks as our column headings. Okay, so I'm just using the first letter of each thing to represent those. We actually don't have to label them, but it can be useful just to get an idea of what's going on. And then we're just a matter of going through. So as we said, Vanita, she's got 8 hours for designing, 10 for purchasing, 6 for cutting, and 5 for sewing. Stan, we've got 9, 8, 7, and 10 as his values. Ebony, 4, 9, 8, and 6. And Philip, 5, 10, 7, and 3. And so now that we've got our cost matrix, our Hungarian algorithm goes through processes of reducing by row, then by column, to try and achieve a possible allocation. So remember, the aim of this is to get a 0 in each row and each column, because a 0 represents a possible allocation. So firstly, we're going to do our row reduction. Okay, so with our row reduction, we're concentrating on each person in the row and looking at their shortest time. And we're going to subtract that value from all of their other times in that row. So if we look at Vanita, 5 is her shortest time. So we're going to subtract 5 off everything in Vanita's row. So that would make it 3, 5, 1, and 0. Now, as you're working through these, you should always get in your row reduction a 0 for at least one value, because you are subtracting the smallest number from everything in that row, means that something should end up at 0. So now when we look at Stan, his shortest time is 7, so we're going to subtract 7. And so that makes Stan's row 2, 1, 0, and 3. Looking at Ebony, her shortest time is 4. So we're going to subtract 4 from everything in that row. So that makes her values 0, 5, 4, and 2. And finally, Philip, his shortest time is 3. So we'll subtract 3 from everything in that row. Makes his values 2, 7, 4, and 0. Now, some of you might look at that and go, okay, well, can't we just allocate? If a 0 means a possible allocation, can't we just allocate the jobs to the people that have the smallest time possible? The problem we have at the moment is that in our matrix, our second matrix here, there is no one who has a good allocation to the purchasing. And if Stan has been assigned to the cutting of the material, well, he's the best person to do the purchasing, but he's already got a job. The other problem that we have is that 2 people have the sewing as their best option. and we can only have one person assigned to each of the 4 tasks. So at the moment, we're not in a position to be able to allocate appropriately. And so our next step, after we've done our row reduction, when we check our information here, we need to do what is called a column reduction. So step 3 is a column reduction. And that means we are basically doing the exact same thing, but now we're concentrating on the smallest values in each column. So if we look at the designing column, the smallest number is a 0. And so when I subtract 0, nothing will change. So that first column, the numbers will actually stay exactly the same because I'm subtracting 0. When I look at the purchasing column, the smallest number is 1. So I'm going to subtract 1 from all of the values there. So that makes it 4, 0, 4, and 6. When I look at cutting in column 3, again, the smallest number is a 0, not going to change anything. And column 4, with the sewing, same thing. Smallest number is a 0, not going to change anything. So I just transfer those values as they are down into my matrix. So I've got the full picture that I'm working with there. And so now with my column reduction, I can see I've got that other option that has appeared in Stan for the purchasing. But again, I don't have necessarily a complete version of possible allocations. So at this point, our next step is to do the lines, okay? And remember, the lines is a technical way, or it's the step in this algorithm, which is the version of setting out the possible allocations on a bipartite graph and checking whether it's possible to allocate. So when I want to draw the lines, so if I just write it here, draw lines, I have 4 tasks. So 4 tasks, 4 people, which means I need to, when I'm ready to allocate, I need to use 4 lines. When I look at my graph here, I'm aiming to draw a line, either a straight horizontal line or a straight vertical line, so that I'm knocking out the zeros, and I need to be as efficient as possible. So I might draw a line across this second row, down the 4th column, and I've got 1 left here. So let's go across that 3rd row. So at this point, I only used 3 lines. So I'm not ready. Okay, I'm not ready to allocate yet, which means I need to go on with step 5, which is subtract the smallest uncovered numbers. So looking at my graph here, or sorry, my matrix here, the numbers that aren't crossed out, the smallest number that is uncovered would be the number 1. So I'm going to subtract 1 from everything that is uncovered. So again, set up my 4 by 4 matrix. The numbers where the lines are won't change. So I can write them back in to begin with if I want. And it's just now the numbers that are uncovered that I need to worry about subtracting from. Okay, so if I'm taking 1 off each of them, in the top row it's going to become 2, 3, 0, and the bottom row it's going to become 1, 5, 3. So here I've picked up a 0, another possible allocation. So at this point I want to test my lines again. So step 6 is redraw lines. So again, that's just my shortcut for checking if I'm ready to allocate. So this time I might draw across the top row, second row, and I can't knock out those 2 zeros in any way without using 4 lines. Okay, so this time, 4 lines, I'm ready. What that means that I'm ready is that I can now go and allocate. So there's a couple of ways of allocating. I'll show you using a bipartite graph first, and then I'll show you a different way using the matrix. So with your bipartite graph, we take our people, so Vanita, Stan, Ebony, and Philip, and our tasks, designing, purchasing, cutting, and sewing. And everywhere we see a 0, so in Vanita's line row, her possible allocation is to cutting and sewing. Stan could do purchasing or cutting. Ebony can only do designing, and Philip can only do sewing. And then it becomes our process of elimination. So you look at the people who can only do one possible job. So Philip can only do sewing. Ebony can only do designing. Because Philip does the sewing, that means Vanita now only has one option left to her, which is cutting. Because Vanita does the cutting, Stan only has purchasing available to him. And so there are our 4 allocations for the 4 tasks for the people. And so at this point, in order to answer the question, we've now got our allocation, but to answer the question, we go back to the original information, the original cost matrix or the original diagram. But let's go back to the cost matrix, and we're going to have Vanita cutting. We've got Stan purchasing, Ebony designing, and Philip sewing. So you can see there a couple of these were what we had guessed would be the best allocation to begin with, but then this algorithm has allowed us to be able to assign the rest of the jobs and guarantee that we'll get the smallest amount of time. And then so looking at calculating that time, we're actually going to do 6 plus 8 plus 4 plus 3. So that gives us our total of 21. So here, our total time (6, 8, 4, and 3). So 21 hours in total. Now, a different way, rather than using the bipartite graph of allocating, is to use the final matrix you end up with. Remember I said a 0 is the equivalent of one of these connections. So the way I would allocate from this matrix, this final matrix, is a very similar way. If I look in the row, if someone only has one possible allocation, so a 0, that means they have to take that 0. Okay, they have to take that allocation. So I can see from this, Ebony goes to designing. I might just add those labels back in as well. So that helps us. I then can see that Philip, the only possible allocation for him is sewing. Because Philip's doing the sewing, this 0 here for Vanita is no longer required. It's not going to be used. So we look and she has only one other option here, which is cutting. By the same token, if Vanita's doing the cutting, Stan can't. And so his only possible allocation is then the purchasing. This method still does require you to go back to your original cost matrix and identify the original times, but it's just a different way of allocating from the diagram, okay, into the matrix form. So use whichever version you would prefer to use. I think most of us find it easier to draw out that diagram and be able to visualize, or especially when you're doing it with elimination, to see what the final answer is. Okay, so as I said, that is just a worked through version of those examples from page 32 onto 33. Have a practice at these. It is a method that you do need to know how to do and demonstrate in your exams, particularly exam 2.